So I'm going to just try to quickly present to you a research program that I'm involved in and a lot of other people are involved in, and that is studying information processing in general probabilistic theories. One motivation for it being to better understand the nature of quantum information processing. So what it is we're trying to characterize quantum theory and classical theory maybe within a broad framework of what Rob Speckens likes to call foil theories, theories that contrast to them, help us thereby better understand their properties. And in particular, want to achieve this understanding, this contrast in terms of the flow and processing of information that these theories permit, the nature of it. Why might you want to do this? Well, there's actually some pragmatic reasons. Maybe it would help us develop quantum protocols or even classical ones. Understand the limits to quantum information processing. Maybe model the way information behaves in other complex or concurrent systems where maybe the restrictions that make it not exactly like classical probability are imposed by engineering or something like that. And then there's the more hubristic reasons, of course. A lot of people think perhaps information is the essence of quantum physics. Maybe by thinking about informational principles, we might get an analog of Einstein's principle-based account of special or general relativity. I don't really know how likely that is, but it's a possibility worth looking into. So the founders of quantum mechanics often did realize that they were making an informational break with classical physics, this notion that measurement disturbs the state. Schrodinger's characterization of entanglement is a beautiful one. The best possible knowledge of a total system does not necessarily include total knowledge of all its parts, not even when these are fully separated from each other and at the moment are not influencing each other at all. He's thinking about entanglement in terms of states of knowledge. The fact that you can have a pure state of a composite system that has mixed marginals. There are already some illuminating characterizations and axiomatizations of quantum mechanics. There's no reason we can't have many different ones, even in terms of information processing. And the point here is to understand the nature of information in quantum mechanics and thereby the nature of quantum mechanics itself, not necessarily to have the one derivation. Maybe there will be one that's recognized as obviously the best way to understand it. I don't know. So a lot of these derivations that already exist, some of the assumptions are very natural and beautiful mathematically, and we don't yet have that much understanding of the operational implications of them. And part of this project is to try to get more understanding of, for instance, the fact that the state space of quantum mechanics is self-dual, homogeneous, properties like that. Okay. So the probabilistic approach, whatever else they are, quantum states are compendium of probabilities for the outcomes of all measurements we might make on them. And quantum effects, as we call the elements of positive operator valued measures, the positive semi-definite matrices between 0 and the identity, they're just compendia of their probabilities in all states they might occur on. And so this is a good framework for studying more general theories. Now you might think, well, fundamental theory shouldn't be about probabilities of measurement outcomes. And I can see why people often take that point of view. Well, we may not know what quantum mechanics is really about or how it should be formulated, but still, studying the structure of these probabilities may help us understand it. Maybe quantum mechanics is a theory for how small subsystems of the universe look to other somewhat larger subsystems, probabilistically, and maybe it's not the final structure of the universe. Okay, rough overview of formalism. We've got systems. Systems have convex sets of states, which determine the probabilities of measurement outcomes. And then there are convex sets of measurement outcomes. So I've written the states of the mega. These are what's called an initial interval in an ordered linear space. UA is the uninformative measurement outcome that has probability 1 in every state. And then there's a bilinear map from pairs of a state and outcome to probabilities. Why do we want it bilinear? Basically because we want to be able to take mixtures of state preparations, and we think the probabilities will be a mixture, the same convex mixture of the probabilities that would have been given by each of the states, and vice versa for measurements. Okay, convex set of allowable dynamics. Maybe we'll want a way of making composite systems or recognizing compositeness within a structure. C is A tensor B. Or maybe we'll want other additional structures, group actions acting on these things. This A tensor B is starting to look a bit categorical. And you can put this into the kind of categorical framework that Bob was talking about earlier today, and we're starting to do that. Okay, main results, which is probably all I'll really have time for. And these are main results, I should say, that my collaborators and I have come up with. There are actually plenty of other interesting results in this theory. I think the right way to think about more general correlation theories, like Dan was just talking about is in fact as a case of this convex framework. And some people are doing that and getting interesting results. And so the derivation of Searle-Elson's inequality, in a sense, can be thought of as an example of this kind of result in this broad program. Okay, so a set of states is clonable. That is, you get independent copies of the state. Omega goes to omega tensor omega, where these are not necessarily quantum states, but we have a good notion of what this means. If and only if it's, the states are perfectly distinguishable, and in that sense, classical. A set of states is broadcastable, which means the copies may be correlated or entangled. The marginals are all the same as the original state, if and only if it's in the convex hull of a set of clonable states. So it's in a sort of a classical subset of states, because these things, convex hull forms a simplex, whose vertices are perfectly distinguishable. Convex subset of the state space. Classical subset of the state space. And again, the only information you can obtain without disturbance, disturbing some state, is intrinsically classical information. So it's information about which superselection sector, if you like, the state is in. And the notion of superselection selector has a good definition as direct summand of cones in this framework. Other examples, exponentially secure bit commitment, which is not possible in pure quantum theory or pure classical probability theory, is possible in any non-classical theory that does not have entanglement. I guess Barnum, Dawson, Lieber, Toner proved that. It's in Information Theory Workshop 4 2008 by IEEE Proceedings. Necessary conditions for conclusive teleportation. We've come up with sufficient conditions for deterministic teleportation. There's a paper on the archive by me and Alex Wills, Matt Lieber, John Barrett. It's not, we haven't published it anywhere yet, but you can find it on the 1ph. Conditions for ensemble steering, so the so-called generalized Houston-Joseph-Wooters theorem. If you know what that is, and if you don't, it just says, so in quantum mechanics, any ensemble, any probabilistic mixture for a density matrix can be obtained by taking, there exists some bipartite entangled state, such that if you make a measurement on this other wing, the conditional states on the, let's say, Alice's side, conditional on the results of Bob's measurements, give you that exact ensemble for the state, any ensemble. So we know what this is. Basically, you have entangled states of a particular type, which are also very useful in doing teleportation, in fact, such that if you think of the state as a map by conditionalization, the map is an automorphism of the cone. So I've just tried to give you a flavor of the kind of thing you can do in this framework, and I think it's a very productive way for understanding what quantum mechanics, how it behaves, maybe coming up with new quantum protocols, and really understanding its nature and how it might fit in with the rest of the physics we have. So thanks.